What's up, everybody? My name is Demetri Kofinas, and you're listening to Hidden Forces, a podcast that inspires investors, entrepreneurs, and everyday citizens to challenge consensus narratives and to learn how to think critically about the systems of power shaping our world. My guest in this episode of Hidden Forces is Dylan Patel, a semiconductor and AI analyst and the founder of SemiAnalysis, a boutique semiconductor research and consulting firm that provides cutting-edge insights into the semiconductor supply chain, bridging the gap between business and the chips industry. Dylan and I spend the first hour of our conversation going over the latest information we have about Huawei's groundbreaking new 7nm chip produced by Chinese semiconductor foundry SMIC, what it tells us about the progress that China's domestic chip industry has made in the years since the U.S. Commerce Department implemented a series of targeted updates to its semiconductor industry export control measures, and the military and commercial implications of all of this for America's strategic competition with China. In the second hour, we focus our attention on how exactly China's domestic chip industry has managed to make so much progress despite the stated goals of the Biden administration. What can be done to strengthen the existing export controls that are already in place, and what additional measures can be taken to complement those efforts that strengthen America's own semiconductor industry and that incentivize a rebuild of American industry and society for the 21st century. If you want access to all of today's conversation, and you're not already subscribed to Hidden Forces, you can join our premium feed and listen to the second hour of today's episode by going to hiddenforces.io/subscribe. All of our content tiers give you access to our premium feed, which you can listen to on your mobile device using your favorite podcast app, just like you're listening to this episode right now. If you want to join in on the conversation and become a member of the Hidden Forces Genius community, which includes Q&A calls with guests, access to special research and analysis, in-person events, and dinners, you can also do that on our subscriber page. And if you still have questions, feel free to send an email to info@hiddenforces.io, and I or someone from our team will get right back to you. And with that, please enjoy this deeply informative and timely conversation with my guest, Dylan Patel. Dylan Patel, welcome to Hidden Forces.
Thank you for having me.
I'm excited to geek out with you today, Dylan. This episode is we're recording this a few weeks later than I would have liked, but it's also given me a chance to learn a bit more about the subject of today's conversation. But before we get into that, which I'm very excited to talk about, Huawei's new phone, SMIC, China's domestic chip ecosystem, and the efficacy of export controls, and their implications for electric vehicles, I want to learn a little bit more about you. How would you describe to the audience what you do, what your background is? You're obviously the author and editor and founder of SemiAnalysis, but tell me a little bit about you.
Sure. So I founded SemiAnalysis in 2017 after I was working in the industry and such. This SemiAnalysis is a semiconductor supply chain research and consulting firm. We work directly with companies in the space. And so I started it with myself. Nowadays, there's myself and there's three others across Singapore, Taiwan, and Japan, sort of across the world. And we're all pretty technical folks, but we get into the supply chain analysis and technology, competitiveness of various folks, chips, manufacturing processes, cost structures, et cetera.
What made you want to start this blog? What was the sort of opportunity that you saw in the market, and who is your audience?
Sure. So, I'd been doing consulting and such from 17 on SemiAnalysis, but I had no online presence really. It was sort of mostly word of mouth type stuff. And then in 2020, COVID happened, had a WordPress blog. And then in late 21, and this was occasionally posting maybe once every other month or once every few months, right? And then, just whenever I had time, when I was bored to write something. And then in 2021, late November, someone didn't pay for reports. I was like, well, what do I do with it, right? So then I made it a paid piece online, and it really garnered interest. So I was like, okay, well, let's try and do more of these really technical pieces that dive into the supply chain, that go much deeper, and we can try and monetize it better. And so that's been really successful. And the main group of people that read it is kind of diverse, actually, right? So I would say it's like one third, one third, one third, right? One third is actually, semiconductor, industry, right? Industry folks. The next third would probably be folks that are interested in investing or learning more about it, but don't work in semiconductors directly. And then the last third is sort of the AI folks, because we've done a lot on the AI supply chain, manufacturing wise, what's the bottlenecks and equipment for that, and so on and so forth, as well as like how the models work and what they require on hardware. And so we've done a lot of work there. So, about one third of the readership is also in the AI field. But I would say investors, whether public market, private equity, venture capital, retail investors, one third semiconductor, one third AI folks is sort of the general breakdown. But yeah.
A lot of smart people read your stuff. I know that because they've sent it to me. So you published a post, as I mentioned it, a couple of weeks ago titled China AI and Semiconductors Rise. U.S. sanctions have failed. And it was in response to the news of Huawei's new 60 Pro 5G phone. I don't think they've actually confirmed that it's 5G, but I guess the breakdown confirms it's 5G, but they didn't actually announce that it was. And you wrote in this piece, quote, "As we approach the one-year anniversary on the October 7th China sanctions, it is abundantly clear that the export controls are failing. Put simply, Kirin 9000S, which is the 7-nanometer chip powering Huawei's new phone, is a better designed chip than the West realizes. Even with the lackluster export controls, this is a leading-edge chip that would be near the front of the pack in 2021. Yet it was done with no access to EUV, no access to cutting-edge U.S. intellectual property, and intentionally hampered. We cannot overstate how scary this is." What have we learned about China's domestic chip industry from the release of this new phone, and what about that would lead you to describe it as, quote, scary?
Yeah, so back in 2020, 2019, right, Huawei was right in the front of the pack, right, with their phone chips, with their infrastructure chips related to 5G telecom, right? And specifically on phone chips, right, they were releasing chips that were on par with, Qualcomm and Apple. But a lot of the IP in those chips was American, and they were manufactured by TSMC, Taiwan Semiconductor Manufacturing Company. And so, while it was impressive, right, the IP was, either American or also British, right, ARM. If you've heard of that company, ARM, UK-based company, and it was manufactured at TSMC using tools that are mostly from, US, Dutch, and Japanese origin, right? Which is, was impressive. And then the ban hammer came down, right, if you will. And that was before the October 7th restrictions on Huawei, right? And it was like, okay, well, Huawei's can't use TSMC anymore, and so they were really roadblocked. They weren't allowed to access a lot of the IP.
That was back in the middle of May 2019? When the initial sanctions,
yeah.
But that was after the whole kerfuffle that happened in Canada with the CFO, the daughter of the CEO and founder of Huawei, being detained.
Exactly. Well, that was all part of the same saga, and the ban came down, but the ban was like, hey, you have a year, to get whatever you need, and then you're done, right? And so that's sort of the whole same kerfuffle, right? In 2019, 2020, I think end of 2019 is when they were stopped with shipments, and then when 2022 came around, 2023 came around, Huawei was still like completely vacated the market, right? In whether it be a lot of infrastructure related stuff, a lot of mobile stuff, they were not really making anything. And then come around, October 7th restrictions come down because it's not about Huawei anymore. It's about like some other capabilities that are being developed in China. With regards to SMIC, which we'll get to, you could think of them as China's TSMC, not as good, but, a lot closer than people realize. And alongside, many other companies in China. And there was a lot of fear around AI, around high performance computing, around like simulations of, missiles and war and things like that the Chinese government was doing that, the US wanted to prevent. And the U.S. has gotten Japan and the Dutch to sign onto some of these regulations as well with regards to some of the equipment bans.
Didn't they make some additional restrictions early this year? They implemented some additional restrictions that I think the U.S., Japan, and the Netherlands were on board with early this year, didn't they?
Correct. So the last year on October 7th, the U.S. released basically unilateral sanctions, right? Just us. And then early in the year, the Dutch and the Japanese sort of signed on board to a version of that, right? Not everything, but certainly a version of that. And some of the details are, specific to the Dutch and the Japanese because they make certain equipment that the US doesn't, right? And so the thought was that for many, many pundits was that China couldn't do anything, right? And they were going to be held back from manufacturing, any advanced semiconductors. And so that was an incorrect assumption, I believe, because, even back in March, we explicitly said that those restrictions had many loopholes. And we just put out a blog post about that. And it shows that it's true when we see this chip today. In January, we put out a blog post about this. And the restrictions were made, but they were, a lot of folks, especially in DC, I think just assumed that this was going to work completely. And it did work for some companies. Some companies are completely dead. For example, YMTC, which is a memory company in China, was actually designed into the iPhone, was designed completely out, right? And they're not shipping to, many folks at all anymore. So there are some cases where the restrictions really worked, but in the main, most important sort of case, which is advanced semiconductors for, processing, right? Think of smartphone, think chip, think AI chip, those sorts of areas, digital logic, right? The export restrictions have clearly failed because China is still able to manufacture. And what's surprising about the chip that Huawei did is, it's a phone chip. I don't think people are too concerned that phone chips are a national security issue, but it's what it says about the general capabilities of China, right? So some of the things about this chip are, it's not just the IP that they use to design the chip, right? The CPU cores, the GPU cores, the image signal processing, a lot of this sort of stuff has no more US or UK IP in them, right? They've designed their own custom architecture, right? I think that's really important, right? It's not just, hey, can they manufacture? It's also, can they design their own custom architecture? Two is that the fact that they can manufacture a chip of this quality, right? And by quality, I mean, hey, it's literally in between a 2021 Qualcomm chip and a 2022 Qualcomm chip.
Now, explain to people what that means, because a lot of people are going to hear this, they don't understand that. So break down a little bit what that means when you're talking about the quality of the chip.
Yeah, so chip design is, tremendously complex, right? If you think about, a lot of times people throw out the word transistor. You can think of a transistor as an on-off switch, right? And modern day phone chips alone have 15 to 20 billion transistors, right? On-off switches perfectly arranged to make everything about them work, right? Whether it's communicate data, render images, play games, what have you, right? They're perfectly arranged to do that, right? So designing that is very difficult, and manufacturing that is very difficult when you manufacture it. Such an advanced capability, right? 7 nanometer for SMIC. And so when you build a chip like that with your own design and your own manufacturing, that speaks volumes to the capabilities you have, and you do it at high volume, right? SMIC just came out yesterday and said they're going to ship 7 million of these phones this year, right? That is not low volume. That is very high volume, 7 million phones. Now it's, far cry from the annual, shipments of Apple, but, they're supposed to get to 40 million phones next year, which is, gets a little bit closer, right? Apple ships something like 200 or 250 million phones a year. So the volume is there. It's a real high volume product. The quality is there in terms of performance of the chip, right? How fast is it? How efficient is it? How fast are the data speeds, right? With 5G, all of these sorts of things. Can it play games? Can it take good pictures, right? And process those images from the phone camera, right? All of these sorts of things point to the chip is very good. And somewhere in between a 2021 phone chip and a 2022 phone chip for Qualcomm.
2021, the year, and 2022. So the implementation of the chip is like pretty much on par with a lot of existing phones that are out there today. But in terms of generations of chips, they're, what are they, like 1 to 2 generations behind? The leading edge is 3 nanometer.
Yeah, I mean, Apple just released the first 3 nanometer chip, and there's a lot of issues with regard to overheating that you might have read about on the internet even regarding that. But, more importantly, right, like Qualcomm's chip that is 2 years old was produced on Samsung's 4 nanometer, right? And so the fact that they're beating this 4 nanometer chip, the 7 nanometer chip, speaks testament to the design yet again, right? We talked about that a bit in the, more in detail, but the fact that they can produce something and design something that is on par with what Qualcomm was making just a generation ago, right, is a huge deal. And one that feeds forward to other types of chips that I think the US government is more worried about, right? High performance computing, AI, things like that. That's where, it sort of gets scary. And the point is that they failed, because if they can do this, it's not a long jump to go to the next point, right?
So when Qualcomm developed 7 nanometer chip, did it do that with DUV, or it didn't have EUV, right? They did it with DUV machines.
So let's back up a little bit, right? The whole manufacturing process, right, is, you have many tools, about 1/4 of which are lithography tools, right? And lithography is dominated by the Dutch, although there are some Japanese companies as well, like Nikon and Canon.
By the Dutch, you mean ASML?
Correct. ASML in the Netherlands. And so the ASML's big rate climb to fame was that they made immersion lithography, about a decade and a half ago, right? Their first version of immersion lithography. And that's when they jumped ahead of the Japanese companies, Nikon and Canon, right? Nikon was actually the leader in the world. They had greater than 50% market share, more like 60, 70, up until ASML made this breakthrough. And then more recently, in 2019, ASML was already shipping their new version of lithography called EUV, Extreme Ultraviolet. And they have 100% market share there, right? In DUV, which is the prior version, they have high market share, but not 100%. In EUV, they have 100%. And so 7 nanometer technology is sort of right on the line, right? Whether you need this new lithography or not, right? And I say new lithography or not, the old one, it continues to be upgraded and improved. So it's not like that one doesn't have, any line in the sand. It's not 2005 tech, right? Or 2007 tech. It's actually still 2023 tech.
By old, you mean deep ultraviolet?
Correct. DUV, deep ultraviolet. And so 7 nanometer, there's sort of 3 companies that manufacture leading edge semiconductors in the world up until, very recently. Now SMIC has been added as the 4th. But TSMC, who has the majority of the market share in Taiwan, right? They have a 7 nanometer. Intel has a 7 nanometer, Intel in the US, and they manufacture in the US, Ireland, and Israel. And then there's Samsung, who manufactures mostly in Korea, but they do have a big plant in Texas. And of those 3 companies, all 3 have made 7 nanometer technologies. TSMC and Intel were able to do it with what's called multi-patterning DUV, deep ultraviolet, right? So that just means they use the DUV lithography many times, right? For simplicity's sake. They use it many times and they're able to get to a high volume, high quality 7 nanometer process technology. Samsung wasn't able to figure it out with DUV. They had to go to EUV, but there's still also, high volume, high quality. TSMC makes the best though, 7 nanometer technology.
But TSMC relies on DUV or EUV. And are you better off relying on EUV if you have the machines because it's more efficient?
Right. So TSMC, to this day, even though they have over 50 EUV tools and they make hundreds of thousands of wafers a month with EUV, still uses DUV for their 7 nanometer. Right. They had a version with EUV, but it wasn't as good. It was a little bit more costly. So they went back to DUV, and the vast majority of phones, right? Every Apple 7 nanometer phone was DUV, right? From TSMC. Intel, every 7 nanometer laptop chip or server chip you get is DUV, right? It's only the Samsung 7 nanometer chips that used EUV. And the question is whether you're better off or not. I think, TSMC's as a clear example, having tried both, right? Samsung only ever tried EUV, Intel only ever tried DUV. TSMC tried both, right? And so at 6 nanometer and 5 nanometer, they use EUV, but they think cost efficiency wise, yield, right, which is how good the product's coming out, how many are good, how many need to be thrown away. The yield is better, the cost is better, the performance is better with DUV rather than EUV.
That's so interesting because that would have been my question. My assumption was that the yield would have been better on EUV, and one of my questions outstanding on this was how good could the yield expect to be on these new Kirin chips produced by SMIC, given the fact that they're using DUV?
Yeah, so on TSMC 7 nanometer, using DUV technology, right, they were able to, and they have had over 95% yield on many chips, right? Dozens and dozens of designs from, every chip company you can think of, as well as, like, hey, Google's AI chips and Microsoft's, various chips and Amazon's various chips, as well as, every semiconductor company you can think of, right? Also has used TSMC 7 nanometer or still does. And those are all, very high yield, very high performance, very good, high quality, right? And so there's, and the reason why you would think EUV is better yield, let's back up a little bit for those who don't fully, understand lithography, right? Lithography is basically how you make the pattern on the chip, right? You tell it, you expose the wafer, and it's like, okay, I want lines here, or I want holes here. And then you go through a bunch of processes of deposition and etch, right? Depositing stuff on the wafer, removing stuff from the wafer, and you're able to build up layers. And you're able to say, hey, where the lithography tool said I needed a circle, right? I'm going to build a circle made out of copper or aluminum or some other material, right? And around it, I'll put silicon dioxide, right? I put down and remove materials depending on where the lithography tool tells me. Now, if I want to make a 7 nanometer chip, right, that resolution, a chip has many, many layers, right? It's a bunch of transistors and then a bunch of layers of wires over them, right? And you need many, many layers of lithography, right? 7 nanometer requires about 60 layers of lithography. And so those 60 layers of lithography and then all the associated deposition and etch tools are defined by what is the pitch or what is the feature size I want, right? If I want to make this feature at this size, I need to pattern it with lithography. Okay, well, DUV lithography cannot do that in one go. You cannot just say, hey, I want a hole that is, 36 nanometers wide, right? A diameter of 36 nanometers. You cannot do that with DUV lithography, right? You can do that with EUV lithography, but DUV lithography is so mature, so high throughput, so much lower cost, right? Talk about EUV tools, $160, $170 million now from one single tool, right? Is $170 million about. And a DUV lithography tool is significantly cheaper than that, and it's faster, right? And because there's so much experience with it, actually it's like, hey, well, it's like I can measure 4 times before I ever cut, right? If you think of it that way, right? It's a technology called multi-patterning, right? Double patterning is using the DUV lithography twice to make one feature, right? To define where one feature is and then depositing and etching for that one feature afterwards, right? And then quad patterning, right? So 4x patterning is when you do it 4 times. So it's kind of the whole adage of like you measure twice, cut once, right? In this case, to make a 7 nanometer compatible feature, you have to do quad patterning, right? So measure 4 times and cut once, right? To bring it to sort of a, construction sort of terminology. The actual process is a lot more complicated than that, but it turns out that you can get better cost and yield with DUV at 7 nanometer, at least based on what TSMC believes, who's tried both and who is the best at manufacturing in the world.
So what do we know now, or what do we think we know about where SMIC may be in terms of yield per wafer? And what could we expect them to get to once they've run this process enough?
Sure. So I see no reason, going back to the whole point about DUV technology, right? The tool that TSMC used in their 7 nanometer process technology, and same with Intel, was the 1980i. It's a specific model, right? And that tool is not banned under any US restrictions, any Dutch restrictions, or any Japanese restrictions, right? The 1980i. And it was released in 2018, I believe, it might have been 2016, but it's been updated multiple times, right? There's the 1980i, there's 1980 BI, CI, DI. I think they're on the FI by now, right? The most latest version is the FI.
Just quick question. So ASML is one company that produces this tool, but what other companies produce DUV?
So Nikon also produces tools that are not quite as high quality as ASML's, but still very high quality.
But this particular tool is produced by ASML that we're talking about here.
The one we're talking about here is ASML, because ASML pretty much, while they have something like 95% market share, that on technologies like 7 nanometer, it's basically 100%, right?
I got you.
So in 2018, when TSMC started their 7 nanometer production, and then they've upgraded over time, right, with, what's called P, right, N7P plus effectively, right, later in 2020, that process technology used the 1980i. Which has been updated and upgraded over the years to all the way up to the FI, right? I think that's the 6th iteration of it. The important thing is TSMC is able to achieve yields of over 95%, right? Usually when you start production of a new technology, you're maybe 60, 70, 80% yield of a chip. But over time, you get higher and higher and higher as you just practice, you do more and more, right? Process improvement. And so the question is, how high can SMIC get? Well, at least on the lithography standpoint, as well as on many other standpoints, right? With regards to deposition tools, etch tools, right? Because remember, lithography is only 1/4 to 1/5 of the market, right? There's many other tools required to manufacture semiconductors, metrology, deposition, etch, those tools.
So is lithography integral to the entire design process, or is it essential just for those higher end chips?
No, so lithography is done on every single chip, right? Lithography doesn't actually put anything on the wafer, right? It doesn't put copper on the wafer for electricity to be conducted through it. It doesn't put anything on the wafer, right? On the chip. It just tells you where to put stuff, right? Is the way you can think of it, right? Tells you where to put stuff or where to remove stuff from, right? You might put a layer of copper or put a layer of something across the entire wafer, right? And then you might say, lithography, go, right? Tell me where I want to remove the material, right? For this design of the chip. Okay, this is where I want to remove the material. Okay, now let's put it to another tool that's made by, say, Lam Research, which is an American company, or Applied Materials, which is an American company, or Tokyo Electron, which is a Japanese company. And that tool will actually remove the material where it was defined by the lithography tool. So lithography is required for every chip, right? It's just what level of technology is required. And it's the one that defines the pitch of the size of the feature, right? So it is in many ways the most important one, because otherwise you're just depositing and removing materials sort of across the whole chip, the whole wafer, right? The whole chip without bias or care for where, right? Lithography is letting you do like, oh, the line here, right? So you can actually define the chip. You can actually make the specific features of a chip, right? Otherwise you just have many layers of materials stacked up on top of each other, and that doesn't do anything across the whole chip. So TSMC is able to get to well above 95% yield with the same tools. And in fact, TSMC probably hasn't upgraded the tools because their engineers to the FI, the DI, right? Because their engineers are working on 5 nanometer and 3 nanometer, right? Their best engineers, where SMIC's best engineers are working on 7 nanometer, and they have access to the 1980 FI, which ASML just released, right? The DI, which ASML just released like a couple of years ago, right? Which was better than the original tool that TSMC had when they made 7 nanometer.
So just to be clear, so we're talking about the DUV machines, and these machines are not part. What is the regulation around the export controls? Because I think you can still get a license for DUV, right?
Correct, right? So it's not that you can just ship any tool willy-nilly. There's a bit of a, like a license game here. I mentioned that, right? The US has been handing out licenses like candy. And a lot of the onerous, right, of getting a license or shipping a tool to a company in China relies on that company certifying and testifying that they think that the tool is not being used for restricted technologies, right? 7 nanometer. And 14 nanometer for that regard, right? They think that the tool is not being used there or being shipped to a facility that is making those kinds of chips, right? That are restricted, whether they be AI, high performance computing chips, so on and so forth, right? And so the onus is on the tool company. And if the tool company is like, well, hey, they told us, that it's not for 7 nanometer and, we believe them, right? That's enough to effectively get a license. Now, of course, there's a lot more in regard to this topic, but effectively that's enough to get a license from the US government is the tool company saying, we don't think this is being used for 7 nanometer, and the company making the chip saying, we're not using this for 7 nanometer.
So I diverted us. I want to get back to the question about yield per wafer, but just to clarify something here, when you're talking about tool companies, so a third party will reach out to the U.S. Commerce Department and try to go through the licensing process, and then they will get the tool, and then they will, let's say, sell it to or license it to or lease it to like SMIC, for example? How does that work?
No, so tools, now this is the case for small vendors, but for the major, I like to call them the big 5, it's ASML, of course, in the Netherlands. There's Tokyo Electron in Japan, and then Applied Materials, Lam Research, and KLA in the US. Those 5 companies sell their tools directly. They service their tools directly in the customer's fab and, so on and so forth, right? Because these tools are so complicated, right? I talked about a $160 million tool. Think about how much maintenance there is. It's ridiculous, right? And only people who know how to maintain the tool are the companies who make them.
I see. So ASML will apply for a license to sell to SMIC.
Correct. And some tools that ASML makes have enough US content that the US has to give them the license. In the other case, it's the Dutch regulation. But regardless, both the Dutch and Japanese have set their tool restriction effectively and I'm going to use the ASML tool, but Nikon has a comparable one or tries to have a comparable one. It's called the 2000i, right? Which was released, I believe, in 2021 or 2020. But remember, the 1980i has continued to be upgraded, and there's an upgraded version in 2023, right? And that tool, sort of the line is in between those two, right? The 1980i, which is what TSMC and Intel used for 7 nanometer.
It's the ASML tool.
Correct. And then there's the 2000i, which is the ASML tool, that is sort of the next step up, right? And that tool is what's restricted, but the 1980i is not restricted.
That's interesting. And what is the logic there for restricting the 2000 but not the 1980?
I think the problem is that the industry is very incentivized to sell tools, right? And, before,
understandably.
Again, another sort of diversion, right, is ASML sort of has a stated goal to effectively double the DUV tools that they're going to be shipping and making by the end of 2025 versus 2020, right? And the question is sort of, well, who's going to buy double the tools, right? Who's going to buy double the tools? And they're going to triple EUV, right? So tripling EUV makes sense because, hey, 3 nanometer, I need tons of EUV tools. I need to sell a lot more tools. So TSMC can make them and Samsung can make them and Intel can make them, right? But for DUV, the logic is a bit more questionable. And so they were asked a ton of questions. They kept getting asked questions by investors, right? Like, hey, why do you need to double the number of DUV tools? Like, there's no demand for that. Are you overbuilding your capacity and so on and so forth? So then they did this day where they talked about the semiconductor market, right? And they talked about, why they believe that there needs to be this many tools. And I don't know if you can show people any images, but, effectively they made this whole argument, right? Which is technological sovereignty and competition creates the need for additional capacity, right? And what they said is in 2020, there was very little to no excess capacity in the industry, right? Everything was, most of the advanced chips were made in Taiwan, and TSMC ran at utilization rates well above 95%, right? And the same applied to Hey, Texas Instruments, obviously in Texas, although they have fabs elsewhere, or, they ran at 95% utilization and they had no excess capacity, right? Sort of this whole argument that got us into the chip mess in 2020,
They're saying the
2021.
friendshoring and reshoring dynamics are going to cause a demand pull from countries that need to build up their own domestic industries.
Exactly. And the industry is structurally going to want to have a lot more excess capacity, right? And so their argument is that this is going to happen, right? And I agree it'll happen. But the magnitude of the subsidies from Japan, the US, the EU, Taiwan, South Korea is only a small fraction of this. Really, if you do the math, right, and the sort of market share they project China to have in semiconductors by the end of the decade, most of this excess capacity is Chinese companies building chips that the US or Taiwan or South Korea or Europe already supplies. And, of course, it makes sense for them, right? Like, let me have my own domestic industry. But it's going to create an excess supply dynamic, right? And so their stated goal is effectively, we're going to double the number of DV tools we make so China can make their own chip industry, right? Go from sub 10% market share in the chip industry to somewhere around 30% market share in the manufacturing industry, right? And of course, that 30% is going to displace Western firms, right? Or Japanese firms or Taiwanese firms or Korean firms, right? It's going to displace them, but that's the way the cookie crumbles because those companies are also going to expand capacity, right? Because they have all these subsidies to do so.
But doesn't that directly contradict the spirit of the intentions of the export controls?
I would agree, right? And ASML says it publicly, right? Just go listen to their investor day. You don't even need to go through some back channel. So it's directly in their most recent investor day that they say this, right? Like, yeah, we have tremendous demand because people are going to make excess supply. Oh yeah, China's going to be 30% of the market by the end of the decade. It's pretty clear. They just don't say it.
So they don't say it or they do say it in their public communications?
They say that they need all this and that there's the technological sovereignty and all this.
What explains the mismatch in the public communications between the Commerce Department and what ASML is saying in public?
I think that the reason this is because when the Commerce Department drafts or any other, industry body drafts a regulation, they're like, well, we need to ask the industry because they know, right? We don't, right? Semiconductor manufacturing is so complex, right? Like it's very easy to, for example, in the October 7th restrictions, I went through it with a fine tooth comb and just posted my thoughts about it back last year, spent the whole weekend. Funnily enough, one of the banned tools is something that was first is from 1998, right? Like IBM first put it into production in 1998. It's like, yeah, that's banned. It's like, well, they probably just didn't consult people in the industry because as scared and hawkish as even I would be, right? I'd be like, that makes no sense to ban, right? 1998 technology. So sort of there's a mismatch in it's so complex. So you have to be very specific on what you ban. But then how do you do that without talking to the industry? And so the industry is going to focus on the 5 or 6 key points that they need, hey, ban the 2000i, don't ban the 1980i, right? Because that 2000i is needed for this level of technology, 1980i is needed for this level of technology, right? And if TSMC were to start over and do 7 nanometer today, maybe they would use the 2000i, right? Right? ASML is probably right in that regard, but that's not what was, reflected in the market, right? What actually happened, right? And what's actually needed. So sort of the industry will whisper their things and make sure that they get to have China remain as a 30% customer or grow to a 30% customer in the future or more, right? And so they're incentivized in one direction to enable that and say, hey, yeah, well, we don't think that this is happening or we don't, human nature, right? I think is the way it works.
Mm-hmm. So I do want to get back to this maybe in the second hour, because I think one of the interesting dynamics here is the negotiation. This always happens. There's a negotiation between the regulators and the businesses that they're regulating, and there's a process there. And that process can take even longer when you're trying to regulate an industry as complex as this one. It's the most complex industry I've ever seen in my life. And I should also mention to listeners who don't know this or maybe heard the episode but should go back and listen to it. We did a really comprehensive conversation with Chris Miller back in September of 2022, right before the export controls were put out, where we covered the tech, the business, and the politics of this industry. And there's also 2 other episodes, one with John Pelson on the evolution of Huawei, and another with James Mulvenin on Huawei that came out in 2018 around the time that the company's CFO was detained in Canada, that people should definitely go back and listen to. So let's go back to the conversation about yield. And the only reason I'm going back to this is, well, one, high level, it's a tangible marker of success in terms of their production capacity and competency. But it also speaks to whether or not they can actually do this at scale. So you said right now TSMC is able to produce 7 nanometer chips with a yield of 95%. Just to be clear, that means that out of 100 chips, 95 are good for market, right?
Correct.
The yield right now is estimated at for Go ahead and answer that question if you like. But again, let's get back to like, what is the yield now? Where do we think they can get to? And what does that mean in terms of what they can produce and where this chip can go? And then we could talk about kind of, can they go smaller? Can they get to 5? Can they get to 3? What can they achieve with the technology they have now? And then that'll get us into a conversation of export controls and the response of the U.S.
Yeah, so we've made that sweeping statement, 95% plus yield, but that really is yield is one of the most complex things in the world, right? So one example is that there is no iPhone chip that ships with every part of it working, right? And that sounds crazy. There's no NVIDIA AI chip that ships with every part of it working. There's no Intel laptop chip that ships with every part of it working, right? Because this process is so freaking complicated. You build in redundancy into your chip, right? And that can come in many forms. And you end up usually disabling or having a redundant element, kind of re-enable, right? Sort of for chips. And you have less redundant elements as you improve yield, right? Maybe the first chip on 7 nanometer, you're like, okay, let's be safe. But then over time, you can do fewer and fewer because that reduces your cost if you don't have redundant elements, right? And so the real metric that the industry tends to use is called D0. And what that metric means is defects per square centimeter, right? So you make a wafer. A wafer is 300 millimeter diameter, right? And so, a square centimeter is going to be 10 by 10 millimeters, of course. It's a circle though. So but you tend to have a certain number of defects per that area, right? And that defect could be a broken transistor. It could be 2 wires that shorted themselves because they weren't printed the correct distance from each other. It could be anything. And so, you have this metric, and that metric then determines like, hey, how many defects you sort of have. And then defects are not always like, it doesn't work, it works. A lot of times it's like, hey, yeah, well, it works, but it's really bad performance, right? Like, this transistor was supposed to switch at 5 gigahertz or 2 gigahertz, whatever, the speed of the transistor that's supposed to switch. But in reality, it's switching at, a tenth of that speed. And so it works. I don't know if we would call it a defect or not. Depends on your definition, right? So people play this definition game around defects density, the D0 metric, right? Like there's all sorts of complexity here. But the point being that there's numbers that some folks have said, which is 0.14. And I'm not going to, dive into what that number means. But, there's also images, right? There's Tech Insights, which is a Canadian company, did a complete teardown of the chip. They took, super, super high resolution photos of the chip with a scanning electron microscope, down to the nanometer precision, right? Tens of nanometer precision. And what they were able to find is that the chip is A, 7 nanometer by any technical merit, and B, at least 7 nanometer class, right? And then B, that the chip sort of variation of structures, right? So like if I wanted to make a hole, right? No one ever prints a hole perfectly. The hole might be a little ovular, right? It might be a little squiggly. The lines might not be perfectly circular. Or if I make a line, it's not a perfect line always, right? It's usually at some point in the line, it might be 10% narrower, and another point in the line, it might be 10% less narrow. It might be squiggly a little bit, right? But as long as the wires are connecting and it's not shorting to another wire, it's all good. In the case of the SMIC chip, it looks very good, right? Like the structures of it look good. They don't look to be, having a lot of inaccuracy in the manufacturing process, right, if you will. And so, it's impossible to know the real yield unless you're like working at Huawei or SMIC or in China in general in the supply chain.
Well, can't they do a sample size? I mean, how many chips did they look at?
Well, the thing is, you're only ever shipping working chips, right?
I got it. Of course. That's a great point. Yeah. That's a good
and then
point.
A wafer is going to produce something like 500 chips possible. And then a certain number of those will be defective. It depends on the type of size of chip, right? This defect density measure, right? Because a small, like a phone chip, right? You could get 500 chips per wafer. But a chip like an NVIDIA chip, right? An NVIDIA AI chip that the world's going crazy about, you can only get 50 chips, right? In generality, right? The exact numbers are a little bit different.
Could we estimate what their yield is based on the types of stuff that they're ordering, that they're importing, that they need to produce chips?
Yeah, so that's one of the methods we went about it. We sort of went about it with 3 different ways, right? One is that D0 metric, just the rumors, right, that people had said. Second was looking at these images in detail for many hours, right? This Tech Insights released, to their subscribers, to the people who subscribe to their research product. And the third was looking at the volumes and such, right? So how many tools have they ordered? And you have to do a lot of napkin math to figure this out because no one publicly releases how many tools SMIC is buying from them. But if you look from that metric, right, how many tools and what's their manufacturing capacity and how many phones is Huawei shipping now and is going to ramp up to ship, you can get to their yield is somewhere in the 60 to 70% band, but there's a huge error bar. right? Like no clue, right? Like it's a lot of guessing and estimation. An educated guess would put it in the 60 to 70% range, right?
So what is that for a company that's just producing this chip, like in the early phases of production? Is that really like on par with what you would expect from a TSMC?
Right. So TSMC started out the gate about that much, a little bit higher. But, on the flip side of the coin, right, Intel had a lot of problems with 7 nanometer. Their first 7 nanometer class chips were worse yield, right? Admitted by Intel themselves, right? And then, of course, now they're great, right? Yield is great, but it took time. The best way to learn is by manufacturing a ton, right?
Now, would it help SMIC that they could have learned something from TSMC and Intel that went about this when 7 nanometer was brand new?
Yeah, absolutely. Because, if you look at SMIC's engineers, a lot of them just worked at TSMC
from
before.
TSMC.
They're Taiwanese.
Yeah.
They're Taiwanese natives. In TSMC, they're getting paid, only like 80 to 150K, right? Like USD, right? Which is a ton in Taiwan, but like, in China, they're getting offered like 500K a year, right?
Wow.
And Taiwan has tried to make it illegal for people to do that. But a lot of people, if they don't have that national spirit, nationalism, they're like, hey, wait, I get paid a ton more. They're going to give me an apartment. They're going to give me a car in the best neighborhoods. My kids are going to get to go to the best schools. Like, why wouldn't I do this?
How big of a problem is that? I mean, how much talent are they attracting from TSMC right now?
So I would say most people in Taiwan, I don't know if you've ever been there, but most people in Taiwan are quite, nationalistic in the sense, right? I mean, I'm proud to be an American and Taiwanese people are proud to be Taiwanese, right? That's just the way it is. Not like nationalistic in the sense of like, I want to invade the whole world, but, kind of that kind of nationalism. But
sure,
most people don't do it, but there's enough people that do it that like, hey, like if you look at TSMC's head of R&D and also like all of the people they've managed, like not all of them, but a big chunk of them were Taiwanese people, right? Like, and it's also like disgruntled people, right? Like there was a guy who was next in line to be, sort of head of R&D at TSMC, and he felt he got snubbed by this other person, right? Who maybe was arguably technically better, right? For the role. And so he was like, I've been working for this role my whole life. And, he went to SMIC in like 2012 or 13. And he's a lot of the reason that their program has been so good, right? Is they brought this like super amazing guy who, maybe he would have been the best candidate for the job at TSMC, but maybe he wouldn't have. Maybe he was just slightly worse. He got snubbed. Is his feeling is like, well, screw this. I'm going to go be the leader at another company and I'm going to compete, right? I'm going to show them up, right? And so like, you have people, things like this also happen, right? So people go, right? I'm not saying it's a humongous percentage of the people, but it is enough to, accelerate the program when you also throw on the fact that, hey, China's graduating more STEM engineers than every other country, right? Kind of like combined, at least Western countries, right? All of Europe and US. They're graduating more STEM engineers, STEM people, and then they're being thrown into this, fire, right? Which is, hey, you have enough capital to buy all the tools you need. We accept low yields, right? Just make it work eventually, right? Improve the process. Get us there because it's our national goal. And then you put them under the hand of, a number of engineers. It's not single digits, it's hundreds of engineers who have actually done this at the best companies in the world, right? In Taiwan and so on and so forth. And it's a recipe of course, yeah, we can do this. We can figure this out, right? And we can develop the talent internally, right? And we figured it out, right? We can do 7 nanometer. And so, yes, 60, 70% yield, getting back to that, is not amazing, but it's going to go up, right? Unless something is done, right? Intel had struggles. 7 nanometers when TSMC passed up Intel, right? Some might argue 12, but somewhere in that time frame when Intel had struggles with bad yield and TSMC raced ahead. And now Intel can yield that process, right? But it took time, right? And so, the same will apply to SMIC. They will figure it out, and it won't take but a year or two to get really high yields with the manufacturing volumes that they're running, right? Because if I run, this volume, then I can tweak a parameter on my process, which is thousands of steps, and eventually figure out, oh, hey, this knob I turned, oh, well, it made my yield 0.5% worse. Oh, it made my yield 0.5% better, right? Okay, now I'm going to implement that across the board, and let's tweak other knobs.
So this kind of gets us to a question that I did want to ask you, which is whether or not these restrictions, and I've heard this from people of the industry, could actually be counterproductive in the sense that they accelerate the maturation of China's domestic chip industry. So how realistic of a concern is that? And then actually let's fold that into a more comprehensive question, which is how much of the progress that China has made this far do we, again, this is the danger of like, we're speculating here, there's a lot of uncertainty, but to the degree that we can know this or to the degree that we can speculate about it, how much of the progress that we're seeing out of China's chip industry is due to loopholes in the export controls? And how much of it is due to maybe even the lagging effects of some of the export controls? And how much of it is due to actually innovation that's happening domestically in China? and the attraction of intellectual capital and smart people that are coming in and actually solving this problem because of the urgency of seeing that their industry is under attack.
Right. So even when the industry isn't under attack, China did lead many very complex industries, right? Not as complex as semiconductors, but very complex, right? Examples like solar panels,
electric vehicles and batteries.
Electric vehicles. Yeah, exactly. Batteries. China makes the most advanced, best batteries in the world, right? They make the best electric vehicles. I know Tesla fans might not like that, but at least on a cost per quality basis, they can manufacture, and they export more EVs than anyone else, right?
Including Teslas.
Yeah, exactly. BYD makes way more EVs and they export them than Tesla does, right? And Tesla manufactures, period, right? So there's obviously areas where China is just out innovated, right? And that is the sense of national urgency, right? Because China has 5-year plans. And their 2025-year plan had already been talking about semiconductors. The 2025-year plan was initiated in 2015. It was probably in the process in 2013 to 2015, right? SMIC has been receiving subsidies since I think they were founded in the early part of 2000s, right? SMIC being China's version of TSMC, right, has been getting subsidies since the early 2000s, and they're still getting subsidies to this day. So the argument of hey, they wouldn't have done it if we didn't push them is completely wrong because they already did it in many, many industries.
So you think in your mind there's already an urgency. It doesn't, maybe it's pushed them a little bit, but it's not like the U.S. Commerce Department and the U.S. government, the foreign policy consensus in Washington should be concerned about the export controls actually causing the Chinese to decide to work harder to solve the problem. They're already working on the problem.
Yes.
Okay, so to that point, let's talk about the export controls and let's talk about the lagging effects of the export controls. And then in the second hour, I really want to get into this because I also want to talk about more comprehensively, really, what is the objective of the administration here? How is it going about this? Because you can't, and I don't know that this is the thinking in Washington, you can't just expect to try and hold the Chinese semiconductor industry down indefinitely. That's not going to work. So it's got to be more comprehensive than that. So I'm curious to understand what your perspective is of what exactly the U.S. strategy is in semiconductors. But my specific question, how much of this is actually the result of the failure in the implementation of the export controls? And how much is us just kind of getting worked up over something that takes time to have an effect?
Yes. My favorite analogy to use here is one of a puzzle. Right? Say we've got this big puzzle. Manufacturing a chip requires thousands of steps, and we only remove a few puzzle pieces, right? That is something that you can look at, and you can still make the puzzle, and you can be like, hey, yeah, look, we're missing this puzzle piece. We'll figure out how to make it ourselves, right? That is something that you can do. But if you take away many pieces of the puzzle, right, then it becomes significantly harder to, focus on all my, energy and smart people, the smartest people on a few pieces of the puzzle, right? Because you have to focus on many. And then these puzzle pieces link together. So there's no way, right? If you have two puzzle pieces next to each other, you don't know what the face between those two looks like, right? So it's sort of that same analogy, right? If you only restrict item A, but item A interacts in an ecosystem of B, C, D, and E, then they can figure out item A. Right. And that's sort of the way the restrictions have been taking it so far. And the question is
so they've been too piecemeal. It isn't necessarily that they've been loose. Maybe they've been loose, but they've also not been wide ranging enough in your view.
Yeah, they've been very loose. They've been focused on just a few items, few pieces of the puzzle. They've ignored huge pieces of the puzzle. And they've also been watered down to have loopholes, right? By industry sort of commentary and help. Right, if you will help with the governments, right, interacting with the industry and having them, lead them to what the actual restrictions should be. For example, the 1980i versus 2000i distinction I made earlier. And many folks, including, not just myself, but many folks in the industry as well, think that the 1980i could be used for 5 nanometer, right? It won't be as economical, but it will still be, right? 7 nanometer is completely economical. 5 nanometer, if the lithography element costs twice as much with the 1980i versus the next generation lithography tool, then that on a total chip basis doesn't cost anywhere close to that, right? Because again, the manufacturing cost of lithography is only 1/4 to 1/5. So if you double lithography costs, you're only increasing the total cost of a chip by 10%, right?
But if you're limiting the more advanced machinery, aren't they eventually going to hit a wall in terms of how advanced those chips can become? They're newer
Correct.
chips?
And that wall, depending on who you ask, is either 7 nanometer or 5 nanometer. I believe it's 5 nanometer. I think they can go one more step beyond what the West did and TSMC and Samsung. I think they can go one more step beyond for a variety of reasons, right? Like the tools having been upgraded to the 1980 Fi, being able to do, that's fine if lithography cost is doubled. It only costs 10% more on the end chip, things like that. So I think that's a real big component of it as well. But there is a wall, right? And that wall is certainly China will not be able to make a 3 nanometer with existing tools, but they also have their own companies, right? Like ASML has been hacked multiple times. There's multiple court cases about it where they've even tried to, they've even gotten companies in China, shut down, or they've had employees leave with tons of documents, and that's been proven in court in the lawsuits that ASML has lodged. Like all the designs of the tools. Now it's, having a design and being able to make it takes time, but the Chinese companies are slowly building up capabilities to build the tools themselves, right? Through corporate espionage as well as their own work, right? So eventually they'll be able to have a domestic supply chain for tooling. Eventually they'll be able to have a domestic supply chain for chemicals and inputs into the fab, right? Currently they do not really, but over time they will. And so the question is like, do you give them a stepping stone in the middle, right? Or not? Do you say, hey, you have to figure out 7 nanometer and 5 nanometer with our tools, and then if you want to go to 3 nanometer, you need to use your tools, right? Or do you say, hey, you can't figure out 7 nanometer and 5 nanometer with our tools, you have to try and use your own tools. And we're not restricting that because we can't, but it's a different like level of like jump.
So that's something that I want to talk to you about in the second hour, Dylan, where I really want to get into the export controls and understand more specifically what it is exactly that you think needs to be changed and where we go from here. Like, what does this look like? And also, what is the objective of the administration here? Is this, again, I think that one of the challenges when it comes to stuff like this is that, very few people understand the minutia of industries like this, and yet it becomes a kind of, there's a general arc that is politicized and that media companies need to tell stories about. And so something oftentimes gets lost in that translation. And also there's an impatience around this type of stuff. And are we just a little bit too impatient? And do some of these export controls just need time to work their way through the system? But we're going to talk about that in the second hour. For anyone new to the program, Hidden Forces is listener supported. We don't accept advertisers or commercial sponsors. The entire show is funded from top to bottom by listeners like you. If you want access to the second hour of today's conversation with Dylan, head over to hiddenforces.io/subscribe and sign up to one of our 3 content tiers. All subscribers gain access to our premium feed, which you can use to listen to the rest of today's conversation on your mobile device using your favorite podcast app, just like you're listening to this episode right now. Dylan, stick around. We're going to move the rest of our conversation onto the premium feed. If you want to listen in on the rest of today's conversation, head over to hiddenforces.io/subscribe and join our premium feed. If you want to join in on the conversation and become a member of the Hidden Forces Genius community, you can also do that through our subscriber page. Today's episode was produced by me and edited by Stylianos Nicolaou. For more episodes, you can check out our website at hiddenforces.io. You can follow me on Twitter at Kofinas, and you can email me at info@hiddenforces.io. As always, thanks for listening. We'll see you next time.